Now I'm working at the Institute of Design and Fine Arts at the Lab University of Applied Sciences in Lahti, Finland. So I'm excited to have this session, and we have two papers here. We have 15 minutes for both of the papers, and we have question and answer session after that. So the first paper is an exploration of interactivity and tangibles in blended play environments, and that will be presented by Ipek Kai. Please.
I thought that I will be the second one, but okay. I will share my screen.
The first one was decided to leave out for some reason from this.
Okay, now session. Do you see my presentation?
Yeah, we can see it.
Okay.
Right after that, this and the question and answer section after that. So the next paper will be a new data collection interface for dynamic gesture and sign recognition with leap motion sensor. And that will be presented by Burçak Kam.
Yes,
please go ahead.
I will share my screen. Can you see my screen?
Yes.
Okay. Hello, I am Burçak Kam, and I am a master's degree student in ITU, and I am working with Hatice Köse, my professor. I will present you our study named a new data collection interface for dynamic sign language recognition with leap motion sensor. I'm going to start with a brief intro and mention some related studies. Then I'm going to continue with difference of our approach and methodology. And I'm going to conclude with the setup and our experiments. If you would have any questions, please ask at the end, the question session. Sign language is the communication method of especially hearing impaired people. This video on the right side shows a sample from Turkish Sign Language. In the literature, there are studies to use it as assistive technology for automatic translation systems. This study is aimed to solve the problem of data gathering and processing for such machine learning studies on Turkish Sign Language, which requires huge amount of data. Also, this study is included within a bigger project, which aims to develop an effective communication system based on sign language, and also to use this system in human-machine interaction interfaces. To be successful for this aim, the approach must be easy to use and as much natural as vocal speaking, while being effective, compact, mobile, and robust. To achieve these points, leap motion controller is chosen as the hardware in the study. You may see the photo of the device on the right side. So sign language includes dynamic static gestures, which are simulated by hand, finger, arm, and face. There are multiple different sign languages you may know or you may not know. They are just like natural languages. For example, there's American, Arabic, Indian, Chinese, and Turkish sign languages, which are greatly different than each other. There are multiple studies on the literature for recognition of sign language. In these studies, conventional machine learning and deep learning methods are used. In some of these studies, different and multiple sensor devices are used, like multiple leap motion controllers or Kinect devices. You may see the success rates on the right side. For all of those different recognition approaches, a lot of data is needed to be included in the training process to increase the success rates of the models. To create those large data sets, collection and annotation tools are required because it is a really big burden to collect and annotate the data in absolute manual way. which is a very long and repeated process, as you may guess. This kind of a tool must have an easy interface and include demo videos to make it able to be used by non-experienced users who are actually needed in the process to make the data absolutely independent from the signer. In the literature, unfortunately, there is just one similar study where a tool is created for Kinect and Leap Motion controller. The tool gathers video and text-based data with command line interface. They also created a graphical user interface. You may see it at the right side, right bottom image. But it is just usable for Kinect devices. They didn't, unfortunately, include Leap Motion controller in that part of the study. As a result, the tool gathers 125 features per frame from Leap Motion controller. So as the approach in our study, we designed and developed a data gathering tool, especially to be used for machine learning and deep learning models. Our design includes very simple interface with several precautions to make the data as much error-proof as possible, especially while it is used by non-experienced users. Also, the implementation is developed to make the tool very flexible by easy configurations for additional desired features. These configurations doesn't require any code change. They just require file changes in reference video directory. So it is pretty easy to configure the tool. Also, this tool doesn't require any additional devices or environments like virtual reality or Unity software, of course, other than Leap Motion devices itself and its driver. As a methodology, the proposed tool is used to record a set of two-handed dynamic signs from Turkish Sign Language via Leap Motion sensor. As I just said, it is designed to be easily adaptable for different data than the currently configured sample set. We developed the tool as Windows Form application while using C# language, which made the tool easily usable on Windows devices. We used multiple different libraries and created an executable file for the end user. We are planning to extend this to be usable in other operating systems too, like Linux, Mac, Android, and iOS. Also, we are recommending Leap Motion Visualizer app to be used alongside with the proposed tool to continuously check the sensing status of the device, because the sensing is sometimes interrupted for various reasons. So at this point, I want to briefly explain the Leap Motion controller, this device. The device is very small and light hardware, as you may see. It includes 2 cameras and 3 infrared LEDs for sensing. It senses a 3D conical area above the device, and it creates positional and directional vectors from the raw data. It creates these vectors from the raw data with its uncompromised calculations in its own driver. You may see the required setup while using the application from the photo at the right side. So it is, as you may see, it is a very simple setup. And as a brief explanation, Leap Motion device has to be connected to the computer via USB port, and it has to be placed between the user and the computer on a horizontal plane facing upwards. While the simulation, the user has to keep her hands roughly 10-20 centimeters above the device in the conical area that I mentioned before. The environment has to be indoor for better results, but light condition doesn't have a great effect on the sensing as long as the environment is reasonably lighted. While the experiments, the tool is used in low, medium, and well-lighted environments without any negative effects seen. Also, while using the tool, we recommend the visualizer app of Leap Motion Controller. As I said before, it is to be used as the reference of the status checking, because sometimes, as I said, it is interrupted because of some various reasons. So I will briefly explain the flow of the application. After the application is started, the user has to choose a sign from the list at the left side of the application. After the selection is made, the demonstration video of the selected sign is displayed automatically at the left bottom side. And when the video is done, user has to press green start recording button to start the recording process. After the button is pressed, webcam visualization starts at the middle. As you can see, it is me. And connection checking is done by the tool for device and the driver. If there is no problem with the connection, the tool waits for detection of both hands of the user. When the hands are detected, I mean, when the user showed her both hands, there is a countdown starting at the status pane at the right side, and when the countdown is done, the recording starts. At this point, user has to simulate the sign and press stop recording button, the red button, when the simulation is done. When the button is pressed, the recording stops immediately, and recording stopped info appears on the status pane at the right side to inform the user, and also the webcam visualization stops too. So this is the end of the process, and this can be cycled through. So this process can be done actually repeatedly without terminating the app, which makes the data collections a smoother process if you want to collect lots of data. After the collection of the data, auto-labeling and timestamping are done by the tool while saving the data. The tool files consist of multiple rows as the time frames and multiple columns as the features, which are the data of directional and positional vectors received from Leap Motion's driver. Sometimes, as I said before, detection may be interrupted for various reasons, and this situation creates some gaps in the data. So the tool fills those gaps with a special character before saving the data to make it directly usable for learning methods, because having gaps creates some errors in the in training of the methods. So if they are not filled, the data has to be pre-processed before the training process. We are eliminating this process with this feature of our tool. The tool is currently configured to gather 12 dynamic and two-handed signs chosen from Turkish Sign Language. These signs created by different movements, gestures of 4 different hand shapes, which are proven to be successfully recognizable by a Leap Motion Controller. In our previous study, you may see these hand shapes from the images at the right side. So our data set includes 3 different gestures for each of these 4 hand shapes, and those 3 signs are arbitrarily chosen from Turkish Sign Language Dictionary. You may see the chosen signs names from the list included. So there is Turkish and English versions there. As I mentioned before, these signs are easily changeable by just changing the reference simulation videos in the application directory. So there is no need for code change, no need for any engineer. As the experiments, we collected and processed data by the develop tool, and we used this data for machine learning and deep learning approaches. We ran multiple experiments with this data for Gaussian naive Bayes, support vector machine, k-nearest neighbor, random forest, linear discriminant analysis, multilayer perceptron classifiers, as well as the neural networks as convolutional neural network, recurrent neural network, long short-term neural network models. We are continuing with the experiments, but so far the best approaches are linear discriminant analysis and convolutional neural network. They both achieved success rates over 90%, even we see 95% success rates. So as the conclusion, I want to summarize our study. In this study, we designed and developed a data collection and processing tool for Turkish Sign Language. With this tool, we created a data set which consists of 12 dynamic signs. We trained machine learning classifiers and deep learning models with this data set for the recognition of Turkish Sign Language. And we got promising results, which leads our study to include more signs in the future for broader, even full coverage of sign language, which is basically the ultimate goal. Also, to get more successful results with increasing amount of signs, the tool can be extended to gather data from multiple sensors, like multiple leap motions or even Kinect, and fuse their data into one data set for more features gathered from different angles of the signs, which will solve the issues coming from the device, like there is some errors coming from leap motion device, and this improvement will get rid of these errors. So this is all from me. Thanks for listening. Do you have any questions?
Yes, thank you very much for these presentations. And now we have time for questions for both of these presenters. Actually, I have a question for both of them. I could start now. Well, first of all, for IPEC, I'm really happy to see technology being used without any technical wearables, and also addressing children, and see real social interaction with technology and with real people. I'm just wondering, you didn't mention about the technical implementation. How did you do that?
Okay. Firstly, I mean, in our first phase, actually, we tried to use processing, but with processing, we couldn't take so much data. I mean, we couldn't transmit color and depth information data. Then we continue with Python. So in Python, actually, I wrote all the codes. So we try to, how can we perceive the objects? And without using Kinect or more complicated device, just with the webcam or just with the telephone camera, I mean. Then we come up with the idea, in the beginning, we can just perceive the colors. Then maybe we can continue to perceive the shape of the objects. I mean, I'm not sure this becomes more complicated, but for now, just the colors, I mean, we perceive. And yes, it's really, I mean, the basic framework, actually.
Yeah, this is so cool. Thank you.
Thank you.
And for Burçak, this is, I think, also this is something very much needed in Turkey, this translation system. I was just wondering, how and why did you decide to have these particular 12 signs?
In our previous study, we worked with static shapes of like hand shapes, and we included 18 hand shapes from a previous study, and we we have to somehow limit the signs for this study. So we got the most successful ones from that study. So we choose just 4 of them, and we choose 3 signs for each of these hand shapes. So by this way we created this data set. But we want to, of course, make it broader. Like, this is the initialization of this study. And of course, as I said, our ultimate goal is to cover all of the sign language.
When would you be doing that, and how?
I hope soon.
Okay, thank you very much. Any other questions?
Also have a question for Ipek. And because I found her presentation on blended play environment for children very interesting. And I was wondering if there is something that can be transferred on learning environment for little older children. I was thinking this because, as you also may have seen, in this period, children learning in front of computers is a very hard situation for them.
Yes.
For Ipek, or also for anyone else who wants to think about this?
Actually, in coronavirus term, we really realized that it's an urgent, how can I say, urgent consideration to make this kind of interactive environments that children can access from their daily environments. Like, because we also talk with the school children, how can we adapt this environment for them? Then we came up in that point just in a basic way. In the context of what they learn, like weather or like about the seasons, for example. So we can adapt their patterns to our system. So after their theoretical lessons, maybe they can just play with this kind of environments and to call some patterns and to make some compositions with them from their homes or from their gardens. I don't know. I mean, now for the outdoor settings, it's a little bit hard. But now we try to actually transform our environments for web version, actually. So from the internet, they can just reach this environment and they can use how they need. For teachers also. We try to make it now.
Thank you.
I just commented on chat, Ipek. You can read.
Yeah.
I am in the office and it's an open office environment. I can't speak so much, so I just wrote it.
Okay. Oh, really? I would like to, see it, what kind of work they make it actually.
You should definitely see it, because I also visited it in Tokyo, and they have a huge museum just with this kind of interactions. Yeah, and they have a special section for children.
Mm-hmm.
And that was amazing. You should definitely, I have some photos, maybe I can send you, but you can also see online.
Okay.
Would you have the link online?
It's actually Team Lab. It must be a Japanese company.
Okay.
So yeah, I wrote it on chat, but I will send the link as well.
Perfect.
It's in a Singapore Science Museum. So I will just send it to you. Okay.
Yeah, great.
Actually, now also we are trying to work with the museums in Turkey, but because of the coronavirus, they are closed. Now they are opening, but for children, they are still closed. So we try to make a interaction tool for them to use from their office to reach another children's. So I don't know, we will continue, but it's a little bit complicated.
Yeah, actually, it's really popular subject for the museums right now. Also, art galleries, they are using and involving this kind of technology to teach children art and this and to make them visit the exhibition, so interact with the I don't know, artists, and I don't know, understand the color composition and everything, and the technique as well. So it's a good subject that you can really,
it really is
create great things.
Thank you.
Okay, any other questions?
So here is the link.
Thank you. If not, then I think we will be closing this session on game design experiment, and we'll have a short break before the next one.
Yeah.
Thank you, everyone.
Thank you, all participants and all speakers, and dear Veli Pekarati, for your contributions. I shared the next session keynote speech from Francesca Tosi in the chat section. So we will meet after lunch at 1:30 p.m. with Istanbul time. So see you soon. Bye.
Bye-bye.
Thanks, bye. Thank you.
Thank you, Veli. Thank you very much.
Thank you.
Bye. Bye.